Greetings from Texas. I'm Todd Humphreys, the director of the Radio Navigation Laboratory here at the University of Texas at Austin. I want to thank Xiaohui for the invitation to speak at the workshop on space cybersecurity and resilience. I wish I could be here live, but I have a presentation to give in the Netherlands on the 12th. So my title is Bracing for Interference, Electronic Warfare and its Spillover Effects. The main thesis here is that electronic warfare, which has historically just been a highly classified topic, really needs to be studied more in depth because its spillover effects on civil systems are now fairly obvious, and these are happening far from any battlefield. So this demands more open discussion and research on the topic. This is a screenshot from gpsjam.org showing in red all of the hotspots where GPS jamming and spoofing is active. In green, any place where there isn't any apparent jamming or spoofing. And if the cell isn't colored, that means that no flights were going through that area from which we could extract ADS-B data from which the GPS health is determined. This was the day just before the invasion of Ukraine. This was about a month after the invasion. Not much had changed, except that now flights through Ukraine and Belarus and some parts of Russia were no longer active. Fast forward to a little earlier this year, and you see that GPS jamming and interference in general has become a much bigger problem. It's moved into Eastern Europe, into the area around Turkey, and it's intensified in the Eastern Mediterranean. This is what we would classify as spillover. These hotspots are likely to be the result of the activities, the combat activities in Ukraine, around Russia, and of course in Israel. But they are definitely affecting aircraft and users of GNSS far from these battlefields. Then something very interesting happened about a year ago, September. This is 2023. It was the first clear case of spoofing of commercial aircraft, passenger aircraft. In this case, the aircraft was flying near Iran and was so completely discombobulated by the spoofing that the pilots had to call air traffic control for turn-by-turn directions through radar vectors. What's more, the Inertial Reference System, the IRS, which in some aircraft sits downstream of the GPS unit and pulls in corrections from the GPS unit, got corrupted on this flight. And this IRS is meant to be a backup to GPS, but in this case, because it pulled in spoofed GPS data, it itself was not serving as an appropriate backup. It got so bad that this particular jet almost entered Iranian airspace unauthorized because of the spoofing. And this has reached the highest levels of awareness. This was back in September, the front page of the Wall Street Journal saying that fake GPS signals are filling cockpits, adding risk for air travelers. And you can read that article. You can see that this has become a problem of real concern across Europe, especially. And it doesn't end in the airspace above us, but also in outer space. This is these are the GPS indicators for a constellation of low Earth orbiting satellites. In blue and red indicate where GPS is available for the satellites of this constellation. And of course, the open space around the Black Sea is indicative of jamming in the area, propagating all the way up to low Earth orbit and preventing this constellation from maintaining consistent GPS throughout the orbits. This isn't a problem for this particular constellation because they've got fairly stable orbits and onboard clocks, so they can propagate through this outage with ease. But imagine if this were happening at, say, a dozen places across the globe. It could be a problem for situational awareness in space and also collision avoidance. AST Space Mobile, a Texas-based company, is fielding new satellites that are meant to talk directly to smartphones. The technology here is based on very large aperture antennas, something like 43 dBi gain antennas in space, which focus their energy on a particular, say, sector on the surface of the Earth. But the only way they can maintain coherence across their very large phased array is to ensure that they can stabilize the array, flatten it out. And the way they do this is through GPS. And so we're building ever more dependency on GPS, even in our very forward-looking engineering systems. Not only that, but the cellular network in the non-terrestrial network protocols that are being developed in the 3GPP standards in release 17 and 18 is building further dependency on GNSS. For these networks, the standard now calls for all the user equipment to relay a GPS or GNSS fix up to the satellite in order to gain initial network entry. And I'm dismayed by this because I think one of the lessons of the last couple of years is that it's time for us to wean ourselves from dependence on GNSS, and certainly not to link ourselves with further dependence on GNSS. In response to this alarming recent uptick in GNSS jamming and spoofing, the people in Europe who are in charge of spectrum for Eurocontrol went to the ITU World Radio Conference to complain. This is where they're supposed to go to complain, and they are the people who are supposed to do the complaining. And in fact, a resolution was proposed and passed at that World Radio Conference in 2023 in December, about a year ago. But it wasn't possible to get full agreement on this resolution without introduction of a caveat, which in my view gives away the whole game. It weakens the protections of these bands by explicitly carving out exceptions for defense purposes. Let's read this caveat. The resolution is resolution 676 in WRC 23. Around the bottom here, you see point number 2. It says to take the following actions to prevent and mitigate harmful interference affecting the RNSS, that's the radio navigation satellite systems operating in the frequency bands. These are the GPS L1 and L5 bands. But now it introduces the caveat, without prejudice to the right of administrations to deny access to the RNSS for security or defense purposes. Now, many will argue that that caveat was already in the constitution of the International Telecommunications Union, but it had never been stated so explicitly, especially with regard to these highly protected GPS bands. And so this kind of interference is with us to stay. I believe this explicit caveat implies that state-sponsored radio interference will be around for some time, because any country which claims a defensive purpose can jam or spoof GPS with impunity. And this even includes cases where the effects might be felt very far from that country's borders. So I'd like to get into what it means to be caught in the crossfire of electronic warfare. And for this, it's important to understand what are the purposes and methods of electronic warfare and understand some of the trends in this space. So I'll first talk about the fundamental theory behind electronic warfare and some of the mental concepts that will help you understand the topic. I believe that the interplay between attacker and defender in electronic warfare is best understood in terms of signal orthogonality and probability theory. What do I mean by this? Well, the practical parameter space for EW is 5-dimensional. You've got frequency, time, polarization, and azimuth and elevation. And I believe, the utility of this approach is to recognize that anytime two received signals are sufficiently different in any one or more of these dimensions, the signals can be considered orthogonal to one another. Okay, so that's establishing this notion of signal orthogonality. We could also talk in terms of phase. That's a 6th parameter we could introduce here, but it's so hard to control phase in real-world settings, and wavelengths are so short that I've eliminated it here from discussion, because if you're going to do electronic warfare, it's just very hard to maintain orthogonality in phase. So the defender, the one who wishes to maintain links, communications links or navigation links, wishes to maintain all these links above some SNR thresholds. So the goal for the defender, whose occupancy in a resource grid, you can see to the left and to the right. So the left is a frequency and time resource grid, which you might see, say, in an OFDM communication system. Little blocks of frequency and time are allocated to a particular user. On the right, what you see is a sky plot where the user could be connected to one or more, say, satellites or other terminals that offer some ambiguity about which one it's connected to. So the defender wishes to maintain vital links to all of these thresholds, above all the SNR thresholds for its communications and navigations link. And its best strategy is to force the attacker to assume a diffuse prior across all dimensions so that interference signals, given that they don't know where the resources will be for the targeted communications or navigation link, they will tend to be orthogonal to the desired signals because you'll basically have to be shooting in the dark, and it's likely that your attacking signals won't land directly on the resources being occupied by the defending signals. So this is what it looks like to force a diffuse prior in the frequency and time space. And this is what it looks like to force a diffuse prior in the sky plot. Now, the jammer's goal for its part is to deny the defender's vital links, but do so as inconspicuously as possible. The jammer doesn't want to be too obvious because then it's more easy to find. So the jammer wishes to throw down a waveform, for example, that just knocks out the particular resource blocks being used by the defender, both in frequency and time space and also in the sky plot. That would be the most effective form of jamming in terms of outcome per watt used in the jamming. But to efficiently eclipse the authentic signals, you have to know quite a bit about them. To maximize the overlap between the jamming waveform and the authentic or target waveform, you have to have knowledge of the spatial and frequency and time dimensions, and perhaps the polarization being used by the target waveform. Now, naive jamming, which happens all the time, is conspicuous and ineffectual. It's conspicuous because you tend to have to crank up the jamming power to get any kind of an effect, but even still, you might only knock out a few of the resource blocks at any given for any given jamming campaign. Or maybe you only knock out one of the spatial directions from which the target receiver or transceiver can maintain a link. Even if you decide to use a sawtooth pattern, it might not be much better than a pure tone jamming. Even if you knock out, say, two of the spatial directions, the target link might still have many more options to choose from. Now, spoofing, for its part, is intended to deceive or deny vital links by mimicking the signals that it's targeting. It wants to mimic the authentic signals across all the parameter space, and if possible, across the content of the signals too. So a spoofer, I say that spoofing is the new jamming because in terms of effectiveness and efficiency, in terms of how much wattage you're using, spoofing can be a very effective form of denying service to the communications link. So let's go through this notion of spoofing being the new jamming, and I'll introduce a few of the theoretical concepts behind electronic warfare here. First, let me pose a question. What is the most effective way for a jammer to minimize a target receiver's post-correlation SINR? In other words, if you want to drive the SNR as low as possible, what's the most effective way for you to do that? Well, here's a basic scenario from the point of view of a spread spectrum signal. What we've got here is a mixture of signal, which is denoted by this kind of sync squared waveform in the background in the frequency domain. We've got interference, which is denoted by this sword-shaped interference block. And we've got background noise, which is flat, assumed to be flat, maybe thermal noise in the background. So in the equation here, you've got the signal component, the interference component, and a spectrally flat noise component. So the question, as stated previously, can be restated as follows. Where would I slide this sword to? where would I position this sword if it were kind of narrowband interference, such that I could maximally reduce the received SINR for a spread spectrum system? Well, it turns out that all of these spread spectrum systems work on the principle of correlation against a local replica signal and matched filtering. So you work through the math on this, and what you notice is that the original spreading code takes the jamming waveform, and the two are convolved with each other to yield the interference spectrum. But then the interference spectrum is only sampled at a very small slice around the zero frequency, where the phase tracking loops are just being able to pull in the case of GNSS, the information bandwidth of the signal, which is actually very narrow. And then once you focus on the information bandwidth of the signal, you see that it's the interference spectrum only near this blue vertical line that matters. Anyway, working through this kind of theory, you can fairly quickly determine the answer to that previous question that I posed. And the answer is that a pure interference tone, a Dirac delta tone, aligned with the carrier with the zero frequency of the direct sequence spread spectrum waveform, that tends to minimize the post-correlation SINR. In other words, you want to lay down your Dirac delta tone exactly where the power spectrum of the authentic signal is maximized. So this is at the zero frequency for the baseband waveform of a spread spectrum signal. But there's a catch here. When you're dealing with electronic warfare, you're not just solving an optimization problem in a vacuum or in, say, in an academic paper. You're dealing with a strategic adversary. And it's just far too easy to defeat this kind of jamming, narrowband, pure tone jamming, by notch filtering. So instead of thinking just one step ahead, you must think multiple steps ahead. You have to think about how the adversary will react to your jamming and how your reaction to their reaction will provoke a reaction, etc. So that's why I started this section, the earlier section, off by saying that we need to, if you're trying to defend your links, you need to maximize the uncertainty that your adversary has with regard to your waveform. Contrariwise, if you are the jammer, you wish to maximize the parameter space overlap with the targeted signal, because that means that any kind of filtering they apply will excise also valuable parts of the authentic signal in order to remove the jamming signals. This is also true, say, for communication signals, OFDM signals shown here. Jamming of a few of the subcarriers might not really impair the communications because the other subcarriers can handle the loss by having coding overlays, or even by shifting some of the modulation onto the subcarriers that are not being affected. OFDM is really a wonderfully flexible waveform, and you have to knock out pretty much all of the subcarriers in order to prevent the signal, some information, from getting through. So smart jamming here looks like spoofing, where you would seek to maximize the overlap. This is why I say that spoofing is the new jamming. So the surest way, summarize here, the surest way for a jammer to minimize the target signal's SINR, signal to interference and noise ratio, is to match its distribution across all these 5 parameters I mentioned. Now, even more potent would be to also match the signal spreading codes and the data content. So not just overlap with the spectral occupancy of the spreading codes, but to actually match those spreading codes in the time domain, maybe even in time domain alignment and in the data content. So all of this points to spoofing. You make it impossible to separate the tares without spoiling the wheat, and that is spoofing. So what does this look like in practice? Here you see delayed Doppler space, where we have frequency Doppler on the, say, lower axis and time delay on the left axis. We've got an authentic signal there. This is a GPS signal that comes up at a particular time delay and a particular Doppler. And then there's a spoofing signal nearby. The trouble that this presents to a GNSS receiver is that it may not be able to figure out which one of these two peaks to track, which one is authentic. It may end up simply saying, I can't know for sure which one is going to be authentic, so I refuse to apply to supply a navigation or timing solution. Thereby, you have denied service to GNSS for very little power. If you want to completely overwhelm the authentic signal, it wouldn't be poking out of the noise floor as you see here. Instead, all you have to do in spoofing is to provide some plausible alternatives that will put the receiver, confront the receiver with the dilemma of having to choose between some of these that it can't distinguish. And so it may simply refuse to provide a solution. Denial of service on the cheap. Speaking about cheap, this next section is titled, What Have You Done For Me Cheaply? And we're going to talk about some of the trends in technology that affect electronic warfare. Two technologies, software-defined radio and phased arrays, are disrupting the EW landscape in important ways. And it's not because they're new, they've been around for a long time, but because they're newly cheap. So what do I mean by this? Well, if I have inexpensive flexibility within this 5D parameter space, I can be a much better defender of a vital link or an attacker of a target link. So flexibility is key in electronic warfare. And flexibility is now fairly cheap. Let's talk first about the time and frequency parameters. This is a Xilinx RF SoC, radio frequency system on a chip. And it's a remarkable bit of equipment here. When I started off as a professor here at UT Austin, I ended up buying with my startup package a really capable multi-frequency wideband recorder. It was about $150,000 and wasn't nearly as capable of this, which now you can buy at what I call here 40 dB dollars or $10,000. This is remarkable. It's got 12-bit ADCs with 8 incoming ports, and each one of them can sample at 4.1 gigasamples per second. It's got a powerful FPGA with an embedded CPU. You can do a lot of pre-processing on this. And of course, with 8 channels, there's plenty of receive and transmit that you can do over a wide band. Very remarkable time and frequency agility. What about azimuth and elevation and polarization? This is where phased arrays come in. This is a picture of the Starlink user terminal, which I believe is one of the most extraordinary engineering advances in the last decade. Back in 2019, it was costing Starlink about $3,000, or SpaceX about $3,000 to build each one of these terminals. They were selling them at a loss to their customers. By 2021, it was down to 1.3K. 2024, it's around 600 and maybe even lower. They've got many variants of these now, a miniature variant that is still powerful enough to talk to the LEO satellites. This is extraordinary engineering. I'll get into it a little bit more detail, but what this offers is spatial and polarization agility across a fairly wide band. This covers about 2 gigahertz in the KU band and maybe another 500 megahertz for transmit. And in fact, it's the phased array, the Starlink phased array and its overall protocol that has been key to its surprisingly robust performance in Ukraine. And I'd like to just take a moment to appreciate how the Starlink system works and why it's fairly naturally resistant to interference. First of all, every satellite has 48 downlink beams that it can cast on user terminals and service cells on the surface of the Earth. There are 16 uplink beams. So there's a lot of flexibility here in choice of satellites to assign to service cells and choice of user terminals to assign to satellites. Each user terminal currently only directs a single uplink beam to an overhead satellite. But with so many to choose from, the algorithm that SpaceX uses to assign beams and user terminals can be hopping around and kind of looking opportunistically for the best frequencies, the best satellites, and the best directions. Now, up to 16 beams can service a particular cell. That doesn't mean that each user terminal can be in contact with 16 beams at the same time. No, only one beam is directed from the user terminal to a single satellite. But the user terminal has many to choose from because each one of the 240 megahertz channels, of which there are 8 in the band from 10.7 to 12.7 gigahertz, the KU band, each one of these can be serviced with 2 different polarizations. And so you end up with 16 beams that can service any given cell. And this implies that any user terminal in these spaces could be looking at a possibility of about a dozen of satellites above it, which could service it. And that gives it lots of flexibility. It's not that the user terminal gets to choose. The algorithm on the space constellation side chooses which assignment, but that algorithm can be aware of electronic warfare in a given user area and can be made more nimble to react to the situation on the ground. So remarkably good performance. Russia has been working for more than 2 years to take down the Starlink system and to, say, blunt its advantage, the advantage that it offers to Ukraine. And yet Starlink still continues to be very useful in even on the front in Ukraine. This is a look inside the user terminal. In fact, one of the older user terminals. And I said before, this is a real marvel of engineering. What you've got here is an aperture-coupled patch array with over 1,200 coherently combined elements. So the wavelength here is a couple of centimeters. And you've got 2 different frequencies to service, the downlink and the uplink's frequency. So there's quite a bit of complexity when you're dealing with such a broad frequency band and both downlink and uplink. What they've done is what we call a hybrid design, where you've got multiple beamformer units, 20 of them in this older generation case. And each one of the beamformer units has 23 front-end chips, and each one of those chips service 2 antenna elements. So you've got these clusters that do beamforming initially before any kind of analog to digital conversion. And then after digital conversion, you do further beamforming in the digital domain. This is what it looks on the back, like on the back. You can kind of see the hybrid design in the similar patterns of the rear electronics. So this is a close-in view, and you can kind of see that the larger chips are the ones where the digitization happens, and the smaller chips are still operating in analog. Now, this can be done at lower frequencies, but it's more clumsy. This is a 40 element or 16 dB, about 1 meter array that was developed by Thomas Paine and his research group in Germany. And it shows beamforming in the L band. In particular, this is beamforming at GNSS frequencies. You can see that it's larger, but it can still be fairly effective. However, you have to keep in mind that pure digital beamforming, where every one of the elements is digitized before its signals are being combined with any of the other elements, that is highly flexible. It's wonderful in flexibility, but it's quite expensive. And moreover, it's susceptible to amplifier saturation in hostile RF environments. The point here is that you don't have any protection of beamforming until after the digitization, and that means that these amplifiers can be easily saturated. Now, this is in contrast to the way that the Starlink terminals are built, where you at least have some clusters that are doing analog beamforming, which provide them some protection, some directivity of their beam before the digitization and final amplification occurs. So you can spread out your amplification if you do some mix of analog and digital beamforming. Nonetheless, this is probably the way of the future, even for GNSS. I expect that we will tend to move up to higher frequencies. There are some GNSS frequencies allocated in C-band, and I expect we will see future satellites exploiting those frequencies so that we can get tighter, more compact beamforming receivers to reject interference from other directions besides those from the satellites. Now, cheap beamforming is happening already. This was a GPS phased array recovered in Ukraine around December of 2023 from a Russian UAV. And what they're doing here is that they're passively combining the signals in analog before they ever amplify the signals. So this buys them about 6 dB of enhancement toward the zenith, which often is enough to get a bit closer to the target before you're overwhelmed by the jamming. This is really low-cost stuff, is what I want to emphasize here. And we could go to much higher frequencies. There's a question about whether we can continue to achieve the same sort of performance at these higher frequencies. But these frequencies beckon because the extremely tight beams that can be formed in small packages due to the small wavelengths. But can their costs be competitive with the Starlink user terminal? Not yet, and neither is the performance competitive. Down at L-band, you can supersize this as AST Space Mobile has done with the antenna that you see here in their Blue Walker 3 satellites. It focuses dozens of about 2.5-degree beams onto the surface of the Earth. And so in space, or where you have space, you can supersize this even for fairly low wavelengths. This is, L-band and below. The problem with great flexibility across all these 5 parameters is that you, as a user, also have to enter the network somehow. So you have to enter the network from a cold start in some cases. And during that period, you might be as unaware about the timing and spatial distribution of the network as your adversaries. So this is the Achilles heel. It's the network entry from cold start. You've got to somehow reduce the search space so that you don't spend an inordinate amount of time looking for the signals whose parameters you're unaware of. Now, you might be looking at all of this and see it as a kind of cat and mouse game, destined to go on forever with attack and defense countering each other's innovations. But that's not a fair fight. I want to point out that I don't believe that this is a fair fight because physics, mathematics, and practical considerations, I believe, strongly favor defense in the long run. And I want to advance a few reasons for why I believe defense will prevail. First of all, powerful jamming is conspicuous. We can see you if you're jamming with powerful signals. As you remember, this is the situation just before the invasion of Ukraine. You can still see that even before the invasion, there was plenty of activity in the Eastern Mediterranean. My students and I were curious to see whether we could locate the source of that interference. And we had, back in 2017, installed one of our software-defined receivers in collaboration with Cornell and Aerospace Corp and the Naval Research Lab on the International Space Station. So this was a receiver meant to just do GNSS radio occultation, but because it was a software-defined receiver, we could do a raw recording of the spectrum and send that down and then process it on the ground. And that's what we did, and showed that we could locate the source of that jamming in the Eastern Mediterranean to a couple of 100 meters. And it turns out to have been a Russian-operated airbase on the coast of the Mediterranean in Syria. We published a paper on this back a couple of years ago. After that, we got into what we call direct geolocation. If you have multiple time-synchronized receivers in low Earth orbit, then you can do a much more powerful technique that doesn't rely on extracting the carrier from an arbitrary waveform. So you can deal with arbitrary waveforms, not just ones that happen to look like GPS. And we have been making good use of this too. In a couple of years ago, we partnered with Spire International, which has about 100 low Earth orbit satellites. And we did a dual satellite capture, where over a period of 30 seconds in the southern Mediterranean, we hit record on both satellites simultaneously, and then another recording just as the two were passing into the Black Sea and over Turkey. Using these dual recordings, we were able to find a whole host of interference sources across Syria, Turkey, Iraq, etc., here in the Near East. This is the bounding box for our search. And we found within this many different cases of correlation in the direct approach. This is a very powerful technique that can tease out even fairly closely spaced interference sources. And here you see the results, which were published in a following paper. Zooming in on, say, one of these around Mosul, you find that, yes, indeed, the highest probability spot, according to the direct geolocation technique, is quite close to what appears to be a military compound. This paper was published in April 2023 and actually won the IEEE Ion Walter Fried Best Paper Award for the PLANS conference that year. Going back to this case I mentioned earlier of the first commercial aircraft to be spoofed by GPS spoofing back in 2023. This happened near Iran, and we ended up using some other LEO assets to determine likely spots where the spoofing was coming from. We ended up locating this to the eastern periphery of Tehran in Iran. We can't be sure that these are the signals that spoofed that particular aircraft, but we know that there was a spoofer active right here in this part of the city of Tehran around that same time. And since October 7th last year, we have seen a huge uptick in spoofing in the Eastern Mediterranean. Initially, we thought this was just an extension of the Russian jamming and spoofing that was going on in Syria. But on closer inspection, we found that it was Israel itself, and the spoofing for, say, the most powerful signal that was redirecting aircraft to the Beirut airport was actually coming from an IDF airbase in Israel. Again, we were using techniques from assets in low Earth orbit. Not the direct technique that I mentioned to you earlier, but one that relies on only single satellites at a time. So the main point there was, hey, if you're spoofing, we can hear you, we can catch you, because you'll often be conspicuous. The second point I want to make when I say the tables are tilted in favor of defense is that increasing autonomy allows systems to make do with just a trickle of communications. Consider one of these autonomous ships, such as the ones being developed by Ukraine to, say, cause so much mischief with the Black Sea fleet there in the Black Sea. This is a similar piece of equipment built for the United States. This is an autonomous surface vessel. It's got lots of different sensing, visual sensing, infrared sensing, radar sensing, locally, inertial sensing, plus GNSS in multiple variants, and it's got communications. Well, if you knock out the communications link, you can see here a Starlink-like terminal. You can continue to perform your mission, provided that the local sensing can move autonomously toward the final objective. So autonomy is making electronic warfare a different game, just because now the EW attackers have to cut the lines all the time, continuously block communication, or else you get just a little trickle of information through, and these autonomous systems can work on those orders for long periods of time. Another point is that mega LEO constellations offer unprecedented spatial diversity. This is new. This hasn't ever been the case that we were able to look up and see, say, a couple of dozen satellites with whom we could make contact. So, for example, the Starlink terminal on the autonomous ship here could talk to any one of maybe a dozen overhead satellites. And again, the attacker doesn't know which one it will be in contact with. So it'll be hard to jam in that particular direction. Also, jamming, if it's designed to be efficient and responsive to the environment, has to periodically listen rather than jam. And these quiet periods actually allow defenders a space where they can communicate. This is an actual spectrogram that we took over the Eastern Mediterranean. You can see that there's a lot going on here. There's wideband jamming, there is narrowband jamming, there's sawtooth jamming, and there are radar signals in the background doing their own legitimate things. But what I want to draw your attention to are the deep blue spaces. These are spaces where the jamming isn't affecting, and because of the time and frequency separation here, it's often possible to find one of those deep blue spaces. And that would be, if you're agile, that would be an opportunity to slip a message through. So, zooming in here, it's not always covered by these high-powered waveforms. You could slip a message through in the interstices between these jamming and so forth and interference waveforms. As a last resort, a defender could hide behind the oxygen line. The molecular oxygen line is one where at about 60 gigahertz, as you see in this left-hand plot, the attenuation in dB per kilometer peaks. And this is a log scale on the x-axis, on the y-axis. And so you can see that it really is a sharp peak. This means that signals propagating at around 60 gigahertz don't make it very far. So what does this mean for, say, a connection to a drone? Suppose this transmitter is the drone's legitimate contact for some sort of an operation. Well, with this distance between the two of them and no atmospheric attenuation, you might have a jammer exclusion zone, or in other words, the zone beyond which a jammer of a given power it can operate and it won't disrupt this link. Okay, so as long as the jammer does not operate within this exclusion zone, this link can be maintained. This is again the nominal case with no attenuation in the atmosphere, except that there's wider separation between the transmitter and the receiver, or you know, this link. And that means that the jammer exclusion zone has grown. But now consider a case near 60 gigahertz. The basic rule of thumb here is that if you want to hide behind the oxygen line, the nearest transmitter dominates. So if you can ensure that you will always be nearer to the transceiver with which you're trying to communicate than some interference source, then you can always dominate this link. And you can ensure that the link is maintained. And maybe what you do is you set up a kind of chain of these short such links that would be fairly invulnerable to jamming just because of the strong attenuation near 60 gigahertz. What about escalation? If I've made the case that the defenders will tend to prevail, maybe that frustrates the attackers and will eventually provoke a radical response. Some of you may have read in the New York Times a couple of weeks ago, actually, no, it was just earlier this week, about Cosmos 2553, which is a satellite that appears to be a dry run for space-based nuclear warhead. This is a Russian satellite that is fully capable of carrying a nuclear warhead into space. This is definitely escalatory, but it's not necessarily required to escalate the problems for electronic warfare. You could also simply put an electronic warfare satellite in low Earth orbit, something that has a large power source, such as this 100 kilowatt nuclear power source. It's not a nuclear warhead or anything of the like, it's just a power source. And with 100 watts, you can direct a whole lot of flexible jamming and spoofing to the surface of the Earth. There are signs that there are projects within Russia looking at this kind of LEO spacecraft. But from the perspective of the United States, we have something of an ace up our sleeve too. You might recall this AST Space Mobile satellite I had mentioned earlier, such a wide array in low Earth orbit. This, if you think about it, is an exceptionally powerful electronic warfare weapon. It too can generate something like 50 or 60 kilowatts with the solar panels on the backside, and can direct that energy very specifically and flexibly using its phased array. It's also got a transparent payload so that you can send up from the surface of the Earth what kind of waveform you want it to beam out. And even if it's, 5, 10 years old, it can still beam out whatever new waveform you're creating on the surface. So I see this as, this is just a communications satellite system, but it could have major implications if we ever, as the United States, ever needed to step up and also broadcast jamming or spoofing signals from space. Okay, I will stop there, and I'm happy to entertain questions that you might send me by email. Thanks.